Professor Caffarelli, firstly, we want to congratulate you with being awarded the Abel Prize for 2023 for your seminal contributions to regularity theory for nonlinear partial differentials, including free boundary problems and the Monge-Ampere equation. You will receive the prize tomorrow from His Majesty the King of Norway. We shall return shortly to your mathematics, but first it might be a good idea to know something about your background.
Okay.
You were born in Buenos Aires in 1948.
1948, yeah. In Buenos
So what
Aires.
was your childhood like? How would you describe it?
Well, I was born, I live in an area which is sort of a nice middle class, and basic part of Buenos Aires. So I have when I was a kid and so on, we will play in, they have the houses and then like in any places, right? The place where you can walk and then the cars, right? Mm-hmm. And so we have a place not in the street, but in the, and there have very different class of playing or for instance, we can play soccer a little bit, in this corner. Another typical playing is to throw from the edge a ball or something like that and see who was the closest to the ball. Mm-hmm. And that was already pretty interesting. The beginning is just, but this already was more or less interesting place, right? And then we play more and more like that, more and more complex games, right? Mm-hmm. Where you will take a block of the, always not of the street, but a block of the walking place, right? And cutting in the middle, right? Not cutting, we just mark like that, and you mark in the video, and you're going to throw something flat from some distance and see how close you can get it to this strip or the half of this strip, right? And so that was a game that makes attune a little bit your way of seeing the things with the different distances, right? And then that way you start to get more and more complex issues, right? The University of Buenos Aires, okay?
And there you entered physics, is that correct?
Well, the University of Buenos Aires was science in general. Okay. And you did like, I think I would say, from 15, 16 on for a period, and then became higher, right? And it was, as I mentioned here, to matters of electricity and things like that, right?
But what made you move towards mathematics? Now you're at university, you're studying engineering.
Okay. Well, my father was, was not an engineer, didn't get, because we were he was in a very, very poor area, so he didn't manage to find the engineer thing, but he learned to do matters of engineering, right? And by the time I think he was, I think before I was born, but a few years I was by then, he was an important person in a place that took care of buses and things like that. So he became, in some sense, an engineering or quasi-engineering, right?
Was he a source of inspiration for you?
He was a sort of inspiration, and he pushed to me, with a lot of love, to do some serious things, which would be or engineering or science or something like that. And I followed his advice, and I took the top two courses of mathematics. So I ended up being a professor of mathematics in the top university in Argentina. And this university have interactions with the United States. So I went to the United States to
Minnesota?
To Minnesota, yes. Exactly.
But so your supervisor was Calixto Calderon.
Calixto Calderon, we was sort of in Argentina, but he cooked, entered together with a person there, which was Elia or something like that, I don't remember the name. So from some time I was in both places, and then they just hired me
at Minnesota.
In Minnesota, and had a full professor solutions impressions there.
So what made you choose Minnesota to go to?
Well, at the beginning was because of this connection between the person in Minnesota and the person in Buenos Aires.
I see.
And the person in Minnesota came for some, it was about 2-3 months to the University of Buenos Aires, where was his colleague, and he gave a course, and I chat with him, and I think he liked it very much.
Was this Nestor Riviera?
Nestor Riviera was the one in Buenos Aires.
Oh, exactly.
In the Buenos Aires, and in the new eras starts with Easter. I don't remember. I cannot catch it, but was really a wonderful person.
In Minnesota.
In Minnesota, he, because I just arrived, he was a professor, but not too much fun. He supported me freely for several months until I really get a full profession in Minnesota. And then in Minnesota, I had then a very nice life, because there was a very nice group of scientists, mathematicians, which were all generous. I think it's probably, I think it was sometimes the behavior at that time. I think was a time where science and something like that was not that abundant, and so. But the universities make an effort to maintain that. So we had, I think, in Minnesota, the professors, we were probably 8 or 9, and we were all very well trained, enormous quality of work. So it was a very good time and a good place.
Yeah, we've noticed that many of your breakthroughs come when you change the environment, and now you come to Minnesota. And as far as I understand, Hans Levi was an important source of inspiration for your first breakthrough.
Yes,
the free boundary.
was already at New York. So Hans Levi, I contact with him when I went to NYU. I went at the beginning for I was a visitor or something like that, and I had some connections with him. And Hans Levi was one of his very, I think was an exceptional mathematician, but also was a very positive friend that you can go and ask him mathematics, and if I ask him, do you think I could go to this place or not, he will advise you, sure.
Okay.
Or well, maybe you better go to this other place. So I think it was a time. Still the United States has a very good interaction, the people there. But now it's much more mechanic, everything, because there are, you want Laplacian, and then there are many things about the Laplacian. But at that time, I think the thing was advancing, was at that period. Was starting from much lower than what we have today, right? And then it was a constant discovery in some sense of, what happens with this equation if right-hand side that has this extra term or things like that.
Your first breakthrough, your first discovery has to do with the free boundary problem. And I've taken the liberty of taking this balloon into the studio or the academy here today. And not getting into the mathematics at this stage, we will surely come back to the mathematics. But could you please describe to me the problem at hand? So what is the problem? And I've been told that having a balloon is a good thing when trying to explain what the problem is. Do you want the balloon yourself so you can show us?
A little bit, but
yeah, okay.
Tell you a little bit.
I don't think you can move.
No, well, there's not much I'm going to do. This is a ball with a border and so it is elastic and so on. But what I was chatting this a little while ago, right, with some of the art top here, is I don't want to think of this as a balloon as well as this. If you put so much as you want to blow, it's okay, right? But what was more interesting that I was discussing, and we were discussing before, is, okay, let's start. Suppose you have a circle, right, a ball like that, and then you ask, okay, but this ball inside has, maybe it's filled, it's full of grain, right?
Yeah.
And then if you press it, right, the shape, the form is not anymore this one, right? And if the things inside are pieces of rings in this direction, then things will change. And so more generally, right, we were discussing, suppose you have a ball, but the ball doesn't mean this ball, just a circular thing, right? And then you say inside I have different equations, right? Like maybe you have that there is a square inside where this is fixed, right? And you press on the boundary, then inside, right, there was a complex thing, right? Because,
which is fixed now.
Which is fixed now, right? Or maybe, right, you can have cases where you deform a little bit, and this, you know, it is formed by lines like that. And so if you press, right, if you press like that, the things go like that. Points out. So inside, so now I said, okay, let's do mathematically to a problem where you have these outside things that could be a ball or could be some roundish thing, right? And inside there is a media, right, that is very variable. That means very variable because the action of energy, right? Or maybe because from outside you are putting an electric quantity or something like that. And then that gives you a very exciting, simple, or very exciting problem.
It seems like a very complicated problem.
I know. Well, that's why you spent 8 years linking, you know, flighting with the mathematical variations, right? And makes you like it.
Could I follow up with a question? You can sit down now.
Okay. I'm sorry.
So as we talked about, I mean, this phenomenon that you're studying gives rise to a non-linear partial differential equation.
Right.
And just to put things in perspective, because you have done some marvelous thing within that theory, including what we're talking about now, this work from 1977 with the free boundary. But to put things in perspective, in end of 1950s until the beginning or end of the 1970s, there was a tremendous development in the theory of linear partial differential equations. And actually two names, there were a lot of contributors, but two important names was Lars Hermander, the Swede, and the other was Alberto Calderon. Both of them had enormous influence on that. And so they created, in a sense, a theory of linear partial differential equations, using distribution theory, using the Schwartz space and so on. And my question is the following: are there a similar theory in linear partial differential equation, or is that impossible?
No. There is a relation. The question is the following, right? It is, how could I put it? Okay, in the linear, right? What happens in the linear? I mean, there are many linear.
Oh yes, okay. All right, yes.
But what happens in the standard linear, right? It is that you have this media that it is, like as we were talking, you have a boundary, you have a media, and the media, once you fix it, and this is a linear, the fact that there is a linear function, in general when they say it's a linear function, in the literature say it is a function which is a constant function, right? But one could do linear deformations, right? Divergence of phi of x, gradient u, and phi of x is fixed, and gradient u is fixed, and phi of x was just not depending on u, so u seems to be linear yet, right? Or then this is a linear equation, right? It's a linear equation with a structure which is a little bit not too good because it has, okay, the boundary is the boundary, but I put in the middle some slice, right? Which is fixed, right? And so you have here a linear function, right? But that doesn't make it just the Laplacian, right? You can have any dij of u, right, or something like that, equal to 0, and this is a Laplacian equation, right? But it is a complex one because the coefficient, instead of being just a 1 or a constant, is a coefficient that depends on the position, right? And this was done, as you mentioned, some of the very top mathematicians, right, that have discussed those things. So there is this intermediate thing, which is neither the Laplacian, nor the Laplacian, but they are maybe very, very important because if you have a mediums and you put a plaque in the middle, right, and then you put fluids outside, you can have a linear equation, right? But it is a linear equation in the domain which is the outside thing minus this surface inside, okay? And then it is there is a lot of nice mathematics done on that.
Okay, but of course the standard linear that we were talking about, that's the theory of Hermander, Calderon, and these people. I mean, but if you, for instance, you done, and we get back to that important thing about the Navia Stokes equation that you did with Nirenberg and Kohn. I mean, to solve or to attack that problem requires a different approach altogether than in the free boundary equation. Isn't that true, that these are different, entirely different things?
No, well, what I would say is that the first one, the one you say, the first, the fractional, no. What did you?
No, I'm talking about this free boundary result from 1977 compared to the Navia Stokes equation. Are these techniques entirely different?
I don't think it's entirely different. You know, ones have qualities what the other doesn't have. You know, like you can say, I look at the Laplacian, but such that the equation is zero in things like that, right? That's an elliptic equation, etc. Or I can do another one, which is divergence of gradient of f gradient u is another second order equation, right? It is an elliptic equation, so in sort of a sense it conserves all the things you are accepting, right? The only thing is that you are not letting me use something which is not the Laplacian, right? But if you take the Laplacian and you wiggle it a little bit, you get a DIA, DIJ, and it has all the other things that you can put, that it is that there is an area where it is flat and whatever, sort of almost change in the right way, because you are just bending this a little bit. Instead of the Laplacian, it's not exactly the Laplacian, except the thing you have in the middle. It is almost like that, but you can get one from the other. In other words, you make it the term Bjørn says, well, I can straighten all that and make your Laplacian, right? Okay. So there is, there is this sort of interaction between them, right?
Okay.
Yeah.
About your work from 1977, this work that you did in Minnesota about free boundary. I mean, the people that have looked at that say it's sensational. I mean, it's new ideas, sublime, whatever term they use. Could you explain what you saw that the other people that had looked at this problem didn't see? What was the idea? Can you describe that?
Well, it is the basically ideas in principle is what we were. If you look there, what I did in some sense, I have used, right, the interactions of this to the Laplacian or to this or to this. In other words, it was, if you give me an elliptic equation, right, for instance, right, it depends on what is the elliptic equation. If it is Aij, Dij of u, or what we are saying, divergence of f of gradient u, etc., right? And so I think basically what is in my work is just to look at the Laplacian or the elliptic equations or the variations of the elliptic equations in a different context, right? And this is, for instance, something that appears in, my work and other people's work. But like I say, okay, suppose you have a circle, right? And then you have I'm trying to fix some place here, right, of a problem, and I have this, instead of having these perfect squares, right, I have that everything was broken, right, and then I have that the media here has these densities of space, and it is elliptic because whenever you take a little piece and you turn it around, you can say that the average in this little piece is equal to the value. So it is a Lipschitz function, right, but it is not the nice thing that I begin, right? And so you have to accept it and try to describe when these wiggle bad things of this floor can be fixed just by moving a little bit this, right? But in order to be able to do it, my U has to have a special deformation, and the special deformation is Dij of x, right, times, or D or J of x times J or whatever of U. So in other words, of having the second derivative, U has a deformation of that derivative, right? And some of the work I have done, and which is all other people and our collaborators, to say, suppose I have this floor that is very bad, right? Can I make it a real thing, right? And this in my work is like you have an equation, divergence of etc., and you make a transformation that takes the Laplacian, right? I have several articles like that
Yeah, okay. Well, anyway, you were the one that that saw things that other people didn't see. That's certainly. And let's move now to the Navia Stokes result that you proved with Nirenberg and Kohn.
Yes.
And that's still the best result, which is known about Navia Stokes.
The Navia Stokes.
Yeah, and of course, Navia Stokes is one of these Millennium Prizes that the Clay Mathematics Institute gave.
Yeah.
So Nirenberg has described your co-work with him that he has a fantastic intuition talking about you. Could you say more about that? What does your result about the Navia Stokes say? Can you describe it?
Well, I think it is more or less in a very way the same as what I was seeing here, right? Because what I did with him was to give, he gave me, or we got together some equation which is rather complex, right? And we transform it into a Laplacian sort of thing, into a structure which is very special for us, right? So basically what we are saying, right, is to redo the things, right, to the linear classical things. In other words, because I want something simple to do other things, right? In other words, again, if we have this wiggling that goes around, maybe you cannot walk. If you are an old man, you cannot walk around this. So better I fix it for you, right? Okay, so there is some reasons why you want to deform this. What I did with Nirenberg, right? Basically, in some sense, or in some cases, is to take a deformed quantity, right? And just can we make this, put it with the Laplacian or with the simple equation, right? So that you can do the computation there, where you can do you have an integral in time, for instance, thing. How can you reorganize your thing that is traveling in time to make the simple the situation, right? In other words, suppose that we have a thing that goes around with some fluid, and the fluid is a mixture of fluids of some different qualities, right? And then what we do with him is, well, let's say, can we transform this flow into a constant flow, right? And can you do a translation in which that I can take this and reproduce B, and the other way, if I have B, I reconstruct A, right? And this is important in many applications, right? Actually, because you have from a general meter, because you have some other issue that you have been looking about density or whatever, right? And then you want to say, well, okay, I want to transform this into a flow along a line. Then you have to see if, again, there is a transformation that does that. What does the transformation you can get? Can be the transformation that is just constant all the time, or a transformation where the density decays at the time, right? So it is, it is, I think.
I have one last comment about this before we step to a different topic. This Navia Stokes. First of all, of course, it's a tremendous improvement by a result by Vladimir Scheffer that you did.
Yes.
And what you did, popular saying, is that you don't prove the existence, of course, of solution of the Navia Stokes, but you prove that if there is a solution, then the singularities have to be very, very small. I mean, yes, right. That's the essence of it. So anyway, then
and the force doesn't need to be zero either. The F doesn't need to be zero.
No. Right.
Yeah.
Yes.
But also, this comes, of course, at the time when you're again moving. You're now at Courant in 1980 to 82, and you're in a new environment. But then you start working with, for instance, the Monge-Ampère equation. And as far as I understand, there are some things from your 77 paper on the free boundary that you see again and you apply it to the Monge-Ampère. Is that correct?
I don't remember, but I remember, because Monge-Ampère is not the standard Laplacian precisely, right? It is, but it is, but it was a solid transformation, right, if I remember well. So,
and you have a sequence of beautiful papers here. And Monge-Ampère is something that you come back to several times.
Yes, because it has to do with at the difference of the others, where I just rearrange and whatever it was, right? The Laplacian equation sort of puts everything in the right place, right? I say, in other words, you have to fill this this equation, put it as it should be to be. Yes, I like it a lot. Yeah.
But yeah, okay, and so we can see a continuation of many of your first ideas that are developing through the Monge-Ampere. And if I don't...
Monge-Ampere has the geometric...
Exactly.
Beautiful, yes.
But even, so it continues to a paper in 2010 by you and Vasseur on optimal mass transportation. So it really has a long story in your career. Can you give us some feel of what actually is, what does it say?
What is it?
Yeah, what are the Monge-Ampere equation? How should we think about it?
Well, it's what I mentioned to you, the equation. In fact, if you look at where in my works, it says where it comes from. So in the same way that I said, I have the transform as a function and I transform it using the Monge equation, right? To make it more like a round thing or to make it, so it is a higher level, redoing, let's say, of the quantities. Yeah.
So it says that you close the gap of our understanding by proving that the explicitly known examples of singular solutions are the only ones. And this is in the 90s, I take it.
Yes,
or in the end of the 80s.
Yeah, but it's exactly what we have been doing. So the Monge-Ampere is the one that gets an email that is sort of very complex, and you make the solution, the Monge-Ampere solution.
You have a beautiful paper together with Nienberg and Spruck from '85, where you're talking about the connection with symmetric functions. Any comments on that paper, or is it too far gone? I really enjoyed reading it.
Okay, thank you very much. Thank you.
I would like, or we would like to mention this paper that you wrote with Silvestre, Luis Silvestre.
This is recent. This is
from 2007, and of course he is going to give a talk on Wednesday at the Abel, talks. But this was about fractional Laplacian.
Yes, fractional Laplacian.
And of course it's cited in the maths SciNet enormous, 1,600 times, incredible. But anyway, it's sort of interesting because first of all, when you wrote your first paper, you had Abel in the title. You made Abel summation. And of course, fractional derivation, the first person that introduced it and used it effectively was Abel. He used that to introduce fractional derivation when he wanted to describe the isochrone problem, a generalized isochrone problem. So anyway, so there is a connection with Abel in your work after all.
Okay, well that's why we are here.
Not entirely, but anyway, it's very nice that we could point that out. Yes. A question with regards to this paper.
Yes.
So in your paper there, you say that it's a good this is about fractional Laplacians, which of course go back far in history, but you have this sentence that it aids the intuition to think of this as happening in fractional dimension. And now we're not talking about fractional Hausdorff dimension or something like that, but the source space is of fractional dimension. How does that aid the intuition?
I don't know. I was there and I told myself.
But it is wonderful. All the equations align. So the formulas work out, obviously.
I was at the time at the north of. I was in the north of Chicago, not in Chicago, and I did all of these places, and I was really very happy with them.
It's a beautiful paper. We noticed that some of your breakthroughs come immediately after you've changed affiliation. So could you comment on, more generally, the importance of being in an environment where ideas circulate, and perhaps circulate oneself?
Yeah, well, I think for instance, New York is a typical case where it's not that it changes when you change. I think if you go, work I did in NYU or something like that, I have papers, 10 of them through the time that while I'm there, and then one day I just move and I still have 2 or 3 to write, right? But it's not that I need to leave a place
but you need to
do something new. I mean, I think it's more like it's a continuity, right? And when I change, usually when the change place, I just have done some nice article before, and then I go to the new thing and have new thoughts and have another one.
And new people.
A new one, and new people and all that. But it is not, it's just go through, It's not that I'm leaving one to find a better one. Okay, the one you see in the other place has different ideas, and of course then you have never new things to discuss. But it's not because I am leaving the previous one. Usually when I move, it's for other circumstances, when a family matter, things like that.
What is the role of chance in a mathematical life?
The chance in the mathematical?
Chance, yeah. Yeah.
Well, I don't know if to say 4 or 6.
On a scale of
10.
Of 10, yeah. So it's definitely important, but not all important.
No, yes. Yeah.
Okay, so perhaps we should close in. But before that, so you've had over 30 PhD students, and I noticed very many of them also since you moved to Austin, Texas. So there's been an almost explosion, and 3 graduated in 2022, as far as I can understand. So it's still going strong. So what is your approach to supervision? How do you find projects for all of these?
No, we interact, we go to the lectures, we have a student, advanced students, you proposing to this, and they work and do wonderful work most of the time, and then we get together again, and that's it, right? I mean, we really have put together something that is worthwhile to present, right? I think it's more like the interaction from colleagues and from students and things like that, and lectures, and things is what sort of put me and put everybody together, you know.
But do you know the problem in advance when you agree to take a student, or is it so that it develops?
No. Usually they start with some, like, to give them some basic things to work very well, and then I realize, okay, he will be able to advance, and then I said, well, look at this problem. Where if I put this here and this there, you have that, and they write it, and then maybe I give him another problem to make one which is good for him to get a job, and he gets a job. You know, but it is an interaction, and they really are very, very high quality students. The ones I have had, I was lucky at.
We had to also comment upon how many publications you have got. It's immense.
It's enormous.
300, is it? I mean, publications.
And still counting.
And still counting.
Okay, well.
I mean, on an average, you publish 5 papers every year.
I have.
So,
every time, which is let's say a fourth of the year, I do students that write two times, 1 or 2.
Well, it's incredible. And of course, many of them are joint papers with other people that you write, and you like to work with other people.
Yeah. Yeah, I think I mean, and they are happy. I find them 2 years later when they are professors of something.
Oh, that's great.
And they say, well, you know, professor, great, you know, go ahead. I think it is a very nice interaction, and also there are other professors that always help us, give something or suggest something. So I think it's just a bringing together, a constant bringing together of people and things. And
so you feel that the community is important for?
I think so, and you know, it's a very beautiful. I have been lucky from New York and here in Texas, and of being together, always, you know, let's say 2 or 3 students. So if you have 2 students together all the time, that makes you 2 + 2 4, because they are there to so you always have a group of these students. Sometimes I just let them take that your problem is really close to the one of this one, and they are working by themselves. So it's a nice situation, let's say. It's nice.
And is the field in general so that there is a lot of sharing and freeness of exchange of ideas between?
Pardon?
Them? Is the field you're working in so that there is a lot of sharing of ideas between the professionals?
I have with some of them, you know, usually. I work with the people I am training, but I have, let's say, I have one professor every other 2 days that we work together something. So there is some. Also, if you look at my NSF, the thing there, you will see that there are a bunch of professors that are also.
Yeah, sure.
Yeah. It's a very nice. Situation and life. We have a dozen very good mathematicians that they like to do their work. That they are also very, very good, and we change. And sometimes we help But sometimes the two of us give the problem to a student and just let the student get his PhD and work, and we don't we don't put our name because it's like you take away from the person what he really did and things like that. But it's a very nice, I think it's a very nice situation where we are. The university is good with us.
What are your interests outside of mathematics, inside music, sports, cooking? Do you have any special hobbies?
No, this is another thing. Is I like to cook. My wife is a better cookie, but I am a good cookie. Okay, but I like that. I like to play some soccer if I have some time.
And you play the piano also?
The piano I like. But rather often.
What type of music do you prefer?
Classic or modern classic, right? In other words, this type of music that is really we use all the fingers to play it.
Okay. Well, anyway, on behalf of the Norwegian Math Society and the European Math Society and the two of us, we want to thank you for this very interesting interview.
Okay, no, thank you very much. You that tolerate me all the
Thank you.